Back when you learned how to read and write numbers, you learned about the digits 0 to 9. To write whole numbers larger than 9, you learned that all you had to do was use some combination of these digits, as in 52 and 437. So this way of writing numbers has a name, decimal notation. Why decimal? Well, the Latin root of decimal, decim, means 10, and when you have 10 digits in your notation system, 10 becomes a rather special number. Let's look at the number 437, written in decimal notation, to understand why. We can first break up 437 into 400 plus 30 plus 7. We can take it apart even more so that we've got 4 times 100 plus 3 times 10 plus 7 times 1. Remember learning about the ones place, the tens place, the hundreds place, and so on? This is exactly where that comes from. And finally, we can see how we've got a bunch of powers of 10 embedded in here. We've got 4 times 10 to the 2 plus 3 times 10 to the 1 plus 7 times 10 to the 0. So now you see why 10 is a special number in decimal notation. In fact, we've got a name for it. It's called the base, since it's the base of the exponent in our arithmetic here. Decimal notation is not the only way to represent numbers. In fact, even if we get rid of the digits 2 through 9, we can still represent all of the numbers that we could with decimal. So now that we have two digits, 0 and 1, 2 is our special number, the base of our notation system. The name of this notation system is called binary, since the prefix bi means 2. So instead now of having a ones place and tens place and so on, we now have a ones place, a twos place, a fours place, and so on, going up by powers of 2. So let's see this by doing some counting. So 0 is still 0, and 1 is still 1. However, now that we've got a twos place instead of a tens place, 1, 0 represents the number 2. To get 3, we add 1 to that and get 1, 1. 4, since there's now a fours place, is represented by 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. 8 again has its own place, so it's 1, 0, 0, 0. And I think you get the point. Let's take a stab at reading a large binary number and turning it back into decimal notation, since that's what we're used to. This number in binary reads 1, 0, 1, 1, 1, 0, 0, 1, 1. To figure out its decimal representation, let's start by writing the places under each of the digits. To start, we have the 2 to the 0's place on the far right, followed by the 2 to the 1's place, and the 2 to the 2's place, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, and finally, all the way up to 2 to the 8. Now, if we do the math, that's the 1's place, the 2's place, the 4's place, the 8's place, the 16th's place, the 32nd's place, 64th's place, 128th's place, and finally the 256th place. Whew. So now, if we start multiplying everything together, we see we have 1 times 256 plus 1 times 64 plus 1 times 32 plus 1 times 16 plus 1 times 2 and 1 times 1. So if we sum all of that together, we get 256 plus 64 plus 32 plus 16 plus 2 plus 1, all for a grand total of 371. Translating from decimal notation to binary notation is somewhat tricky, since we need to go from a number that's based on powers of 10 to one that's based on powers of 2. Let's give it a go. Here we have the number 237 in decimal notation. To translate into binary notation, I start by finding the largest power of 2 that's less than it, which is 128. I put a 1 in the 128's place down here in my binary number, and then I subtract 128 from 237. And I get 109. Then I just repeat the process. The largest power of 2 that's smaller than 109 is 64, so I put a 1 in the 64th's place and subtract 64 from 109. To get 45. Again, the largest power of 2 that's less than 45 is 32, so I put a 1 in the appropriate slot and subtract 32. I'm going to move up here to get 13. Moving on, I get 8 as the largest power of 2 now, not 16, so I put a 0 in the 16th's place, a 1 in the 8th's place, subtract, and get 5. Then 4 is the largest power of 2. I subtract and get 1. Now I can finish off the translation easily. I put a 0 in the 2's place and put a 1 in the 1's place. So the result, 1, 1, 1, 0, 1, 1, 0, 1. One thing you might not have expected is that all of the algorithms you learned to add, subtract, multiply, and divide in decimal notation work in binary notation as well. We'll do an example of addition. Here, we've got 1, 1, 0, 1, 1, 0, 1, plus 1, 0, 1, 0, 1, 1, 0. Just as in decimal addition, we'll start from the right and work our way to the left. The only difference is that we carry a 1 if the two digits we're adding have a sum greater than 1, instead of a sum greater than 9, as in decimal. So on the right, we have 1 plus 0, 1. Moving to the left, we have 0 plus 1, again 1. Moving left again, we have 1 plus 1. We write a 0, and we carry a 1. Then we have 1, 1, 0. So we have a 0, carry a 1. Then 1, 0, 1. Again 0, carry a 1. 1, 1, 0, 0 again, carry a final 1. And finally, 1, 1, 1. So we have a 1 and a final 1 on the left. The result, 1, 1, 0, 0, 0, 0, 1, 1. And that concludes our quick introduction to binary notation. My name is Nate Hardison, and this is CS50.